All right, welcome back everyone. Just a quick reminder to the formulas that we gave you last time. For 6.2, and I keep wanting to say 8.2 because that's what I'm used to it in my brain being, even though I've taught from this new text before. It's just stuck. But 6.2, the sum and difference formulas, and we said that we're not going to derive these, we're going to take them at blind faith, but I did point out several places where you could find the derivations if you like. And we said that you could either memorize all four of the Blacking versions by themselves, or I gave you what in my opinion is better, combined versions, and you could just memorize these two things by themselves. It's up to you whether you memorize them independent or combined. I prefer the combined version because of the fact that it goes cosine, cosine, sine, sine. No matter which plus or minus scenario you're in, that's the same. It's only the plus or minus aspect that's different. And it turns out plus leads to minus and minus leads to plus. So the all at once formula just goes alpha plus or minus beta, cosine, cosine, minus plus sine, sine. This part right here is where people can make their mistakes though, and they'll think, oh, if this is a plus minus, then this is a plus minus. But it's actually flip-flopped, so be careful there. Similarly for this sine combination formula, it always goes sine, cosine, cosine, sine, if you keep the alpha betas in that order, alpha beta, alpha beta. So these have mixtures, whereas the cosine formula is just cosines together and sines together. Well, the plus led to a plus, the minus led to a minus, so these do have the same plus or minus symbol in the combination formula. So I said it's up to you which ones you memorize, but you do need to memorize these. Okay, so the first thing we did before we ran out of time was we just had a couple different angles that we might be asked to do this process on. So it's a good idea to understand how to break these up. 15 degrees you can write as 45 minus 30. 75 is 30 plus 45. 120, I gave a couple different options of. And yes, 15 degrees you could certainly write as 16 degrees minus 1 degree, but there's no point because you don't know how to handle 1 and 16 degrees trigonometrically. You know how to handle 30s and 45s and 60s and multiples of 90 and all the other, 210s, 225s, things like that, that all break down to a reference angle with 30 or 45 or 60. Those are the angles you want to try and think in terms of, because then you can just go to those two triangles, the 1, 1 square root of 2 and the 30, 60, 90, which is the 1, 2 square root of 3 triangle, which are on that little cheat sheet thing. Which again is not an actual cheat sheet, it's just saying, hey, this is the stuff you need to know. All right, so let's get down to brass tacks and actually see this now. So evaluate the cosine of 15 degrees without the use of a calculator. So you've got to go, well, I'm not allowed a calculator, and Mr. Beckner said without a calculator, there's only so many different angles we can handle this with. I know how to handle 30, 45, and 60. There it is. I'm half blind. Again, based on these two triangles. I said by memorizing these two triangles, you can handle everything with 30, 45, 60, as well as those reference angles in other quadrants, things like 210 or 150 or 135, all degrees, of course. So we're able to handle a lot of those, and then also we are able to handle 90, 180, 270, 360, any multiple of 90 by using the unit circle and the fact that sine is the y-coordinate, cosine is the x, and tangent's the ratio. So these are the things that we need in general, but now I'm asking you to do the cosine of 15 degrees, which 15 degrees is not on that list anywhere that I just highlighted a second ago. So you go, well, what do we do then? We just put in your calculator. I said no calculator. No. So this is what you do. You try and rewrite this. This is the first concept as a sum or difference of angles, where you would know how to handle the two angles being summed or subtracted. Difference. It just sounds weird to say that way. So 15, we already saw, is 45 minus 30. That is, in my opinion, the best way to handle it. Maybe there's another way you can write it, but it wouldn't be as easy. I can guarantee you that. So then we say, all right, well, this is a cosine with a difference, so we go up to the cosine formula. Now, explicitly, it's this single formula, but you can still use the highlighted version because it's just, all right, well, there was a minus, so we're going to use the, excuse me, I was about to circle the wrong thing there, the plus, because we have a minus where we have 45 minus 30. That tells us we'll use the plus. So again, you don't actually have to use the black version. The combined one is perfectly fine. So I'm going to zoom out just a little bit so we can leave that on the screen to get this. Okay. So the alpha is like A, beta is like B, or X and Y, whatever letters you like. So the 45 is the alpha, the 30 is the beta. So it goes cosine, cosine, sine, sine, with a plus between them. Cosine, cosine, sine, sine. So cosine of 45 degrees times the sine of 45 degrees, then a plus symbol because this was a minus originally. Minus leads to a plus for this formula. And I want to bring it to your attention that I've made a mistake. I said sine because I was looking right here. My brain was 2 steps ahead, but my pen was not. So that's supposed to be cosine, cosine. Again, it's cosine of alpha, cosine of beta. So cosine of alpha, that was the cosine of the 45, then cosine of the 30 degrees. Again, please correct this. Again, I'm sorry, my brain was 2 steps ahead of my hand. Cosine of 45, cosine of 30. Then the plus symbol, because this was a minus, we need a plus here. And then it goes sine, sine. Sine of 45, sine of 30. And then every single one of these 4 trigonometric things we know how to evaluate. So this is just like doing 4 simple problems from the first chapter's worth of material. So we need to know what is the cosine of 45, what is the cosine of 30, what's the sine of 45, and what's the sine of 30. Well, anytime you're dealing with 45s, it's going to be the 1, 1 square root of 2 triangle. The one on the left. So the cosine of 45 degrees, remember SOHCAHTOA. So cosine's adjacent over hypotenuse, so the 1 here over the square root of 2. So cosine is 1 over square root of 2 for 45. Let me see if I can do this. Will that be okay? It's not that great. I don't really want to leave that space there. Let me just pull back a little more. Okay, equals. So again, based on this triangle, the cosine of 45 degrees, red please, is 1 over square root of 2. So that's the cosine of 45. 1 over square root of 2. And then the cosine of 30 degrees, well, that's going to use the other triangle. Just pull back on that a little. There we go. There we go. So the cosine of 30 degrees, so now we're here. I'm sorry, yes, the cosine of 30 degrees, so we're here. So that's the square root of 3 over the 2. So this is times square root of 3 over 2. That was weird that it was red for the first dot. I'm extremely confused about that. So again, cosine of 45 was the 1 over square root of 2. Cosine of 30 was the square root of 3 over 2. Now you might be saying, Mr. Beckner, you left this as 1 over square root of 2 instead of going ahead and saying square root of 2 over 2. Sure, you can go ahead and fix that up. That's perfectly fine. And in fact, I'll do it in the next step. All right, so then the plus symbol for that. Sine of 45 is literally the same thing as cosine of 45 because the adjacent and the opposite match. So the cosine of 45 is opposite over hypotenuse, 1 over square root of 2. Times, then we got to do the sine of 30 degrees. Sine of 30 degrees is opposite of 1 over hypotenuse of 2. So half. So let's just clean up. In red, I'm going to show the change. The 1 over square root of 2 is really square root of 2 over 2, and then the same for the 1 over here. I could have gone ahead and done the multiplications and then clean it up, but I just prefer to go ahead and have it injected that way there. Now just simplify each fraction. So you can multiply square root of 2 times square root of 3 is the square root of 6. Then that's over 4. Plus square root of 2 times 1 is the square root of 2. Over 2 times 2 is also 4. There's nothing you can do to the square root of 6. There's nothing you can do to the square root of 2. This is the answer. You can also combine this as one fraction, square root of 6 plus square root of 2 all over 4, which I think a lot of people prefer. So I'd say the second answer is the better version. But the first one is still correct. That square root's kind of hidden there, isn't it? Let me do a little better. There we go. So this cosine of 15 degrees is really just 4 problems from the last section, from the beginning of last section, last chapter, in fact, as well as a formula that you have to have memorized. So no, you're not supposed to just put this in a calculator. There are ways to handle much more than just the multiples of 30, 45, 60, and 90. We can handle things like 15 degrees and 75 degrees, even though there's no real awesome triangle out of this. Now, what you could do is say, all right, well, knowing this now, I can make a triangle and I can say, all right, here's my, and this is not something I'm suggesting you do. Here's your 15 degrees. Cosine is adjacent over hypotenuse, so that makes this a 4. That makes this a square root of 6 plus square root of 2. You'd have to figure out what this side is, and then you could memorize that triangle. But it's really wacky. I'm not going to say what that side is. You can Pythagorean out if you really like, but it's extremely complicated because this is a binomial of square roots. So it just gets ugly. So again, that's not what I'm saying you should do. I'm just saying that technically you could do that. Maybe you deal with these 15 degrees so much that it's actually quicker for you to memorize a triangle than to have to go in through and do the formula and all these 4 individual calculations. Just depends on what it is you're doing. But in this course, it doesn't become that repetitive, so there's no reason to memorize an extra arbitrary triangle. All right, how about the sine of 7 pi over 12? The sine of 7 pi over 12. Now you might be going, well, shoot, what exactly is that? You could convert this to degrees from radians if you really wanted to. You can multiply by 180 degrees over pi, and the pi's will cancel, the 180 and the 12. 6 goes into both of those, and you can reduce and then multiply by the 7, and at the end of the day, you end up getting 105 degrees. Now, it is my opinion that you should do this. Again, it's the 7 pi over 12 times 180 degrees over pi, so the pi's cancel. And then when you finish that arithmetic, you'll get 105 degrees. Actually, you can say 12 goes into both of these. 1 and 15 times, and then 15 times 7 is the 105. I don't know why I only said 6. Now, the reason I suggest doing that change to degrees is because you are going to have a really difficult time trying to figure out what combinations of pi over 3, pi over 4, and pi over 6 will get pi over 12, or specifically 7 pi over 12. So it's extremely difficult to handle a sum or difference problem in radians, but you would go, well, this isn't some pi over 6 or pi over 3 or pi over 4, so I know it's not one of these 2 triangles because those are pi over 6, pi over 4, and pi over 3. So what I should do to make this simpler on my brain is convert it to degrees and then go and try and figure out, well, what can I add or subtract to get 105? Now you might say, okay, well, I can do 150 minus 45. Okay, you can, and that would be fine. You would be able to get the answer, but you're going to end up using reference angles due to the 150 degrees, and you're just spinning it too difficult. What I would say is try and keep your angles quadrant 1 angles wherever you can, and you could use 45 and 60 to do so here. So you can go the sine of 45 plus 60, or 60, I'll go 60 plus 45. The order does not matter at all, it's just the order I chose. So I'm not saying find the sine of 60 degrees and find the sine of 45 degrees. There is nothing like that. In fact, the formula you can just see at the top highlighted. We're trying to apply this formula, which says we're going sine, cosine, cosine, sine. Since this is a plus, it'll be a plus between them because the signs stay the same, SIGN signs. So sine of 60, cosine of 45, then cosine of 60, sine of 45. This is the one where the sines and cosines are paired together in different angles. So if you have sine of 60, the other has to be cosine of 45. If you have cosine of 60, the other has to be sine of 45. So this will be equal to sine cosine. So sine of 60 degrees times the cosine of 45 degrees. My spacing's a little off there. Let me just try better. That's a product implied there. And then it's going to be a plus, because that's a plus, based on the plus minus formula. And then goes cosine sine. So cosine of 60 degrees, sine of 45 degrees. Maybe you just always prefer writing sine and then cosine, which means you would just swap these two things completely. It would be sine 60 cosine 45 plus sine of 45 cosine 60. So in that instance, you're just swapping the order of the first and second angle there. But remember, how do you get this down? Practice. All right, so from here, it's just 4 trig evaluations using these 2 triangles. Now, some of you may have these memorized. Again, if you've memorized the unit circle entirely, that's awesome if it works for you. I can't stand doing things that way, which is why I build things constructively versus just blatant memorization. All right, so sine of 60 degrees. We're now up on this angle. So sine is opposite over hypotenuse, so that's square root of 3 over 2. So that's the sine of 60. And times the cosine of 45, we already know is 1 over square root of 2, but we even know that it's really square root of 2 over 2. It's better to write it that way, so let's go ahead and do it this time. Square root of 2 over 2 was the cosine of 45. 1 over square root of 2, which is really, when you multiply top and bottom by square root of 2, it's square root of 2 over 2. Then plus, that's so weird. I figured out what it is. The color on the other one is when you do your first mark, it stays the same if these are different. It's really weird. Not that it matters to y'all. Okay. Cosine of 60 degrees. Again, we're up here, so make sure that your adjacent is not the square root of 3. Erase, please. Thank you. That's not what I meant to erase, but whatever. So we're up here, so the adjacent is the 1, the hypotenuse is still the 2, so the cosine of 60 is a half, and then the sine of 45, just like the cosine, is 1 over square root of 2, which is best written as square root of 2 over 2. All right, with the first pair, it's a product, so squeeze everything together. Square root of 3 times square root of 2 is square root of 6. Remember, insides can multiply. Outsides can multiply. 2 times 2 is 4. Plus 1 times square root of 2 is square root of 2 over 2 times 2 is 4. And whoa, what in the world? That's the same answer as what we got before, which you can still combine as write the square root of 6 plus square root of 2 all over 4. Either is acceptable, doesn't matter. So that's interesting. The cosine of 15 degrees is exactly the same thing as the sine of 105 degrees. And it's not that 15 and 105 are co-angles, but the reference angle for 105 degrees would be 75 degrees. And when you put the sine of 75 degrees, its cofunction would be cosine, and that would be cosine of 15 degrees. So the cosine of 15 is the same as the sine of 75, which is the same as the sine of 105 by reference angles and a smart trig class. So did I have to do this problem that way? No. I could have used reference angles. As I've mentioned, in trigonometry, there is generally more than one thing, if not more than 2 or 3 or 4 things to get a problem done. Ultimately, the goal is to understand a consistent set of ways to get them done. But if a problem says to do it a specific way, it's probably because you need to practice that particular method. So I will admit, me personally, if I had this problem with 105 degrees, I wouldn't have done it. I wouldn't have necessarily done it this way, but I certainly could have. I could have said, oh, well, that's 75 and then 15, and I already know the cosine of 15 degrees. But I still can't just take this 105 and break it down to 30s or 60s or 45s. That is impossible by using a reference angle, that is to say. You have to do it this way instead, which feels different, which is why we're going to keep trying it out. C. Sine of 240 degrees. Again, I said the sine of 105 degrees, I wouldn't have done it this way because I already knew the cosine of 15 and I could have done cofunctions. Sine of 240 degrees, I definitely would never do it this way personally. However, I know that I can do it and it's good to practice. So let's see what we get. Especially since this one we can confirm the answer. This one we can absolutely confirm the answer via a different method. So sure, you could say, oh, well, 240 is in quadrant 3. You'd have a reference angle of 60 degrees. You're doing a sine in quadrant 3 is negative. So just do the sine of 60, but make the whole thing negative. That's how we would have done everything in the last chapter. But now we're going to try and break this into a sum or difference. And again, there's a lot of different ways. You could do this with 120 plus 120. You could do this with 60 plus a different number, which I'm not going to get into. I chose to get a little weirder with this one just because the last sign was a plus. Let's do a minus. So my particular choice here, which again, there are dozens of choices for this one, I did 270 minus 30. Again, just my choice. You don't have to do it that way. 120 plus 120, or you could go 90 plus 150. I mean, there's a lot of options for this one. 15 degrees, not a lot of good options. 240, tons of options. All right, so that's a sine formula, so we got to go, same pattern as last time, sine, cosine, cosine, sine. But because this is a minus, there'll be a minus between those products. So we go sine of the first one, which is 270, cosine of the second one, which is 30. Sine, cosine, and minus because that's a minus. And now we go cosine, sine. Don't use the same cosine of 30, sine of 270. You've got to make sure you're changing the angle. So it's cosine of 270 and the sine of 30. Be consistent in the order of the sines and cosines, or be consistent in the order of alphas and betas, one or the other. Mr. Beckner, I'll never memorize this formula. Yes, you will. You just got to do it over and over and over and over. Trust me, memorization takes practice. I know it does. How much space do I have? Okay. All right, so we've got some things to do. We need to know, well, what's the sine of 270? What's the cosine of 270? Well, those are quadrantals. We're not going to use these top two triangles because they're on the axis points of the unit circle, the 90, the 180, the 270. I'm going to go ahead and knock out the 270 stuff. So the sine of 270 and the cosine of 270, which means we're down here. We're on our unit circle. Specifically, we're here, 270 degrees, which has a point of 0, negative 1. So the x value is 0, the y value is negative 1. We said sine takes the y value, cosine takes the x value. So the sine of 270 is the y value, and that's the negative 1. The cosine of 270 takes the x value, which is the 0. Again, that was this bit and this bit. That's all I've done so far. I haven't done anything with the 30 degrees yet. Now we'll do the 30 degree stuff. So it's negative 1 times something and 0 times something. The cosine of 30, so we're over here now. We are over here. So we're doing the cosine of 30 first, which is adjacent over hypotenuse, which is square root of 3 over 2. Square root of 3 over 2. I didn't really need to squish it in that tight, did I? That's okay. And the minus, the 0 for the cosine of 270. Now let's do the sine of 30 degrees. Sine is opposite over hypotenuse, 1 over 2. So 0 times a half. Quite honestly, it didn't even matter what sine of 30 degrees was, because 0 times anything is going to be 0. This was going to go away. No matter what that was, And in fact, you could use that as kind of a shortcut in your own work. You don't even be like, I don't need to know what sine of 30 is because it's multiplying by 0. I'm going to skip that step. Sure, nothing wrong with that. All right, -1 times square root of 3 over 2 is negative square root of 3 over 2. Minus 0 times anything is 0. Subtracting 0 does nothing, so the answer is negative square root of 3 over 2. And that's it. So this is pretty common. When you end up using a quadrantal angle, usually, but not always, one of these ends up zeroing out, because for the quadrantals, one of the coordinates is always 0. You generally have the sine and or a cosine in these formulas, so you're going to have a 0 for one of them. It also usually says you probably could have done it with reference angles instead, but not necessarily. So just an alternate version, I will show this once. An alternate version of C, I could have said that the sine, as I mentioned earlier, the sine of 240 degrees is just plus or minus the sine of 60 degrees by using a reference angle. 240 is here, there's your 240 degrees, which makes this chunk right here your reference angle, which has to be 60 degrees. Well, you're in quadrant 3, so based on a smart trig class, quadrant 3, tangent's the only positive, so you choose the negative. So we say, okay, so this is equal to the negative sine of 60 degrees. So we're going over here. We're on, whatever. Now we're on this angle. The sine of 60 is the opposite, which is square root of 3, over the hypotenuse, which is 2. But there's that negative in front of it, and you get the same answer. So at the end of the day, did it matter which way you got it done? No. Is there a third, a fourth, a fifth, a seventh way to do this one? Yes. There's at least 8 ways to do this problem that I see. And that's just at least. There might be hundreds. I'm not saying I'm going to talk about them or see them all or anything like that. But that's the thing about trigonometry, is that almost every single problem is connected to something else in some way, shape, or form. We are all connected. All right. Let's try another. I know we need some practice with this stuff, and we're going to get even a little weirder with it now. Let's do something that you could call a formula, in fact. You can establish a formula for this. Just say, okay, well, I know I got to find the sine of 130 degrees, which 130 is 90 plus 40. So if I know the sine of 40, I can figure it out by using this formula. Now, again, I'm not saying this is a formula you have to memorize, but it is a formula that some people may choose to memorize because they keep coming across this idea. So your alpha is not, first of all, I didn't tell you had to split this up because you literally couldn't. This is a variable. I had to give it to you this way. So your alpha is x and your beta is pi over 2. So this is unique because this right here is a variable. Our answer is not just going to be a number. It's not going to be some square root of 3 over 2 or square root of 2 over 2 or plus or minus with just numbers. There will be something with a variable in the answer. All right, but it's a sine formula with a plus. So that formula goes sine, cosine, cosine, sine. So it goes sine of the first times cosine of the second, sine, cosine, then it goes cosine, sine. Cosine of the first times sine of the second. And then the plus or minus that's here is the same plus or minus that goes here based on that formula above, which I'll scroll up really quickly. Here it is. It's the cosine formula that the signs, the plus or minus signs, change. Plus leads to minus, minus leads to plus. Subtle differences, subtle details that you have to remember. Now the sine of x and the cosine of x, you can't figure out. That is a variable expression. It's the most basic 2 trig functions, in fact. But the cosine of pi over 2 and the sine of pi over 2 we can using the unit circle, using the quadrantal angles, because pi over 2 is 90 degrees. So this will be sine of x times something. Well, cosine of pi over 2, so we're going to 90 degrees, which is right here. Cosine takes the x-coordinate is 0, so that's times 0, which means that's going to go away. Plus, hopefully that doesn't happen again, the cosine of x times Now the sine of 90 degrees. Sine of 90 degrees still uses the 0, 1, but sine takes the y-coordinate. The y-coordinate being the 1. So times 1. So this goes away because anything times 0 is 0. So you just get the cosine of x, because that's cosine of x times 1. So this is a really cool feature, if you will, or formula. It's kind of like the cofunctions. We said that the sine of 90 minus an angle is a cosine, or the cosine of 90 minus an angle is the sine. We can also say the sine of an angle plus 90 is the cosine. So we could also figure out a formula for this involving cosine. The cosine of an angle plus 90 is what? Maybe it's sine, maybe it's negative sine, maybe it's something else. I'm not going to tell you. Maybe try that out on your own and just say E, not an official problem, but something you could try. What is the cosine of x plus pi over 2? If you do it right, I'll tell you the answer. It's going to end up being negative sine of x. So you can show that on your own if you like. That would use the cosine, cosine, sine, sine formula. It would use the unit circle only. You'll end up with a 0 and not a 1, but close to a 1. And that's why you end up with the negative. So try that out if you'd like. Be a good exercise. All right. So that was the sine formula and the cosine formula. And I said you have to memorize both of those. You have got to memorize both of those. What I will not make you memorize, at least entirely, is the tangent formula. So the sum and difference for tangents. This one's got a little more oomph to it. The tangent of a sum, and I'll do this the same way as with sines and cosines. I'll show the sum formula, I'll show the difference formula, then I'll show them combined. This goes tangent of alpha plus the tangent of beta, there's no 2's in here, over 1 minus tangent of alpha, tangent of beta. So this is a lot more, like I said, a lot more to it. It's a fraction. Whereas the tangent of alpha minus beta, again, no 2's, goes, I bet you're not surprised that it goes tan alpha, tan beta over a 1, and then tan alpha, tan beta. That's literally the same, except the plus in the top and the minus in the bottom flip-flop to a minus in the top and a plus in the bottom. So what that enables us to do is write a combined form, and let me keep my colors consistent. Did I do it in blue? I did it in blue. There we go. So, or combined, combined, the tangent of alpha plus or minus beta, again, that's not a 2, that's an alpha, goes tan alpha. Let's see if we can figure out this. When it was plus here, it was plus. When it was minus here, it was minus. Those are the same. So plus minus tan of beta all over a 1. Then when the original thing had a plus, this down here was a minus, and vice versa. When there was a minus, it's a plus. So this goes minus plus instead. Tan alpha, tan beta. I'm going to make my alphas look a little better. There we go. So me, what do you think I memorized? Yeah, you already know it. I memorized this version. Now, I have it memorized. I am not going to ask you to memorize that entire formula, but what I will ask you to do is memorize the plus or minus patterns. That is what I want you to memorize. That's the only aspect. So I will give you, you will get a short formula sheet for this upcoming test. The first thing you'll see on that formula sheet, I believe, I might adjust it. I adjusted a little each semester, but will be, I'll give you everything except the highlighted stuff here. I'll give you this. This will be on the formula sheet, And then it would be like, all right, well, what do you put here? What do you put here? You'll need to know that. That's what you need to know. I'll give you the tan alpha, the tan beta, the 1, the tan alpha, tan beta in the bottom. Now, it is my opinion that the tangents are the most difficult to do. Why I have that opinion, we will see over the next 2 examples. Some of those techniques that I've mentioned before that always come back up are going to come back up. One of those being having like a fraction divided by a fraction and understanding to multiply by its reciprocal. Some more of those things are rationalizing denominators, foiling of values with radicals. All that stuff is about to come back into play. All right, so example 3, evaluate. And for A, we're going to have, we'll do radians for this one, tangent of pi over 6 plus pi over 4. Now, I don't have to have given it to you in that format. I could have said this is the tangent of, what's that, 5 pi over 12? Whatever it is. Yes, 5 pi over 12. I could have said, what's the tangent of 5 pi over 12? And you go, well, what's 5 pi over 12? What's 75 degrees? Ooh, I don't have 75 degrees memorized in a triangle, so I need to do sums and differences. So then you go, oh, okay, well, let me turn the 75 into, say, 30 plus 45. And that's exactly what is going on here. This is 30 degrees. This is 45 degrees. I just circumnavigated a bunch of that work in the interest of time, and yet I still took the time to explain how it could have been seen. All right, so I already have this separated. It's a sum, so we're going to use our formula that we have memorized in theory, or at least have the plus minus patterns, and you can understand how to apply the rest of the formula. So again, I'd give you this part, the tangent of the first angle, pi over 6, and then the tangent of the second angle, which is pi over 4, and over 1, and then product them here, tangent of pi over 6, tangent pi over 4. So your formula would have tan alpha, tan beta, 1, tan alpha, tan beta, and then you got to figure out what goes here and here, not zeros. All right, so the top one is plus or minus. So because this was a plus, this is a plus. The bottom one switches it though, so it's a minus. The oscillation of signs is at least convenient. It helps us memorize, I think. At least it helped me. So there's only actually 2 trig evaluations we have to do this time, which initially you'll go, well, that's simpler then. It's only 2. All these sine cosine problems, you had like a sine of 270 and a cosine of 270, and cosine of 30 as well as sine of 30. So that was 4 unique trig evaluations. This formula doesn't have 2 different trig functions, it's only tangents. So we see that tangent of pi over 6 twice and the tangent of pi over 4 twice. So that feels like it makes it easier, but it's going to be our downfall after we figure this out. So first, let's figure out what tangent of pi over 6 and tangent of pi over 4 are. I'll write this here for a second. Tangent of pi over 6 being 30 degrees. So we go back to our 30-degree triangle. Tangent is TOA, opposite over adjacent. So 1 over square root of 3. But we know 1 over square root of 3 is bad form. 1 over square root of 3 is the same as square root of 3 over 3. When you do this. Then the tangent of pi over 4, that's the opposite over the adjacent of the other triangle. Opposite over adjacent, 1 over 1, which is 1. So those are the 2 things we'll need. So this is equal to, tangent of pi over 6 is the square root of 3 over 3. So this tangent of pi over 6 was the square root of 3 over 3. Then the plus symbol. Tangent of pi over 4 was 1 over 1, and you might need to write it that way, but let's just write it as 1 for now. Let's see if we can get away with that. Over 1 minus, the tangent of pi over 6 is still square root of 3 over 3. The tangent of pi over 4 is still 1. The first thing you can do is say, well, anything times 1 is itself, so this is just square root of 3 over 3 plus 1, then over 1 minus square root of 3 over 3. Now, there are some advanced ways to clean this up a little quicker. I am not even going to discuss them. Let's go with what you should have seen as pre-calc students. First of all, you got fractions inside of fractions. But this plus and this minus mean that you can't just go flipping and reciprocating. I'm sorry, flipping and changing to multiplication. I just said the same thing twice. Because of that plus and that minus, it's not just a fraction divided by just another fraction. So we can't go flipping and changing the big fraction bar to a multiplication, at least yet. So what else can we do? Well, you're supposed to have learned that when you have fractions inside of fractions with pluses and minuses, you can get rid of all the individual fractions by finding the individual LCD. So looking at this, looking at the denominators of the individual fractions, which I'm circling, those are 3's. So the LCD of the little fractions is 3. You multiply all terms by this. Now, when I say all terms, I mean just the tops of fractions, not top and bottom. So what we're going to do here is, and I'll show that in red, I'm just rewriting everything first. That's a terrible looking 3. Like a B. So we're taking 3 times the square root of 3 over 3. 3 times the 1, 3 times this one, and 3 times this square root of 3 over 3. What I've done here is I multiplied top and bottom by 3. So I didn't break any basic algebra rules. Whatever I did at the top, I did at the bottom. The reason I did this is so that the 3's in the individual fractions go away. So this is no longer fractions inside of fractions. This is just the square root of 3 from this part, then plus, the 3 times 1 is 3, over, this 3 times 1 is also 3, minus, these 3's canceled, leaving us just with the square root of 3. That is a lot easier on the eyes and the brain, and we're a lot closer to the answer, but this is not the answer. A lot of people will stop here, but the reason this is not an answer, you have a square root in the bottom, that's an illegal, I was going to make a sports joke, illegal flag on the field, illegal play on the field, whatever, yellow flag, warning. So we have to do what's called rationalize the denominator. Now, we're used to doing it up here, like 1 over square root of 3, we just multiply top and bottom by that same radical. You cannot do it this way. You cannot just do this. You cannot just do this. You cannot just do this. You cannot do that. Because the bottom is a binomial, the technique is a little different. It's where you multiply top and bottom by the conjugate of the bottom. This will not be the only time you see this. This should not be the first time you've ever seen this either. So let me just rewrite the problem down here in terms of space. So square root of 3 plus 3 over 3 minus square root of 3. So all we're doing is looking at the bottom. I don't even care what the top is right now. So I'm just mentally blocking this out for now. I don't care what the top is. The bottom tells me what to do. The bottom says multiply by the conjugate, which means change the sign between them. 3 minus square root of 3, 3 plus square root of 3 would be conjugates. So that's why we're going to choose to multiply top and bottom by 3 plus square root of 3. So if you forget what conjugates mean, A plus B and A minus B are conjugates. If they have i's in them, you call them complex conjugates. Then you got to foil the top, foil the bottom. The answer in the bottom should just be something like a 5. Or, I thought I had that working. That's weird. Wow, what happened? Or a 4, or a 3, or a 19, 16, whatever. The bottom should just be a number. It should not have any radicals in it. So if when you're foiling this out, if your bottom still has a radical in the end, you've done something wrong. Maybe you multiply top and bottom by 3 minus square root of 3 instead. Maybe you focus on the top, because that would be very easy to make a mistake on, which is why I love this problem, because it shows, hey, Pay attention to the bottom because this was the bottom. These were the multipliers. All right, so foiling the top. Square root of 3 times 3, that's going to be 3 square root of 3. That was this. That's the f. The outer would be the square root of 3 times the other square root of 3. Square root of 3 times square root of 3 is the square root of 9. Yes, if you know that's already 3, go ahead and change it, but I'm just being meticulous. The inner is the regular 3 times the other regular 3, so that's plus 9. The last is the 3 times square root of 3, which is another plus 3 square root of 3. You always want to write the whole number in front of the radical number. Then all over, don't forget your bottom. Now again, the bottom is special. Something special will happen. The top is just whatever happens. So the bottom, the first, the 3 times the 3 is a 9. The outer, 3 times square root of 3 is 3 square root of 3, and it's positive, so plus. The inner, and this will always happen if you're doing everything right, negative square root of 3 times 3 would be negative 3 square root of 3, which you can see the outer and the inner will cancel. That is by design. If that doesn't happen, you've done something wrong. And then the last is, watch your signs, that's negative square root of 3 times positive square root of 3, which is negative square root of 9. Or negative square root of 3 squared, or just 3, minus 3 specifically, however you want to write that. Anyway, I say, okay, well, the outer and the inner cancel here, like we wanted. But the square root of 9, that's still got a square root. Well, it does for now, but the square root of 9 is 3. So no, there aren't any radicals in the bottom, as we hoped for. So let's do the bottom first. The 9 is still there. That 9 is this 9. The outer and the inner cancel once again, but I don't want to leave those scratches there permanently. And then the minus square root of 9 is now a minus 3. This square root of 9 is this 3. How about the top? Well, we have a 3 square root of 3 and a 3 square root of 3. So 3 plus 3 is 6. So that's going to be a 6 square root of 3. We still have that square root of 9 as well. We still have this 9 as well. Square root of 9 being 3. So I'm going to write the 9 first. I'm writing this 9 first because it's my whole number. Then I'm going to go ahead and combine these two, the 3 square root of 3 plus 3 square root of 3, which would be 6 square root of 3. It's like having 6 apples plus 6 apples. It's just our apples are square root of 3. So plus 6 square root of 3. And then I'm going to write this last, the square root of 9 is 3, so plus 3. And someone's going to go, oh, cancel these 9s, cancel these 3s, and nope, that was wrong. Don't do it that way. Russian. 9 plus 3 is 12, so there's a 12 on the top. Then, I feel like I have a sign wrong somewhere. No, I'm good, I'm good. Plus 6 square root of 3. And then that's all over. 9 minus 3 is 6. If you box this up and ship it out, it's wrong. My math lab would say, wow, you have the right answer. It's not in the correct form, which means it's reducible. And that's because there's a common factor everywhere. Remember, you can't just cancel a 9 with a 9 here and then this 3 with this 3 here. You cancel in factors. So it has to be everywhere in the top and everywhere in the bottom. Now, we don't have to worry about this. We don't care what that is, just the outside numbers. So 12, 6, and 6 are all divisible by 6. So you can say 6 goes into 12 2 times, 6 goes into 6 once, and 6 goes into 6 once. Now again, I don't want to leave that scratching there permanently. So that 12 is now a 2. The 6 square root of 3 is now just a square root of 3. Now I'll write this for a second, but I'm going to erase it. I'm going to erase it. That 6 was a 1, but we don't need to write anything over 1. Just leave it alone. So 2 plus square root of 3. The answer is surprisingly simple, and I bet no one was going to believe that that was the answer originally. And if you wrote square root of 3 plus 2, that's the same answer. But with these 12s and 6s, it is reducible. Some of you might have preferred to factor out the 6 from the top. You go 6 parentheses, 2 plus square root of 3 all over 6, then these 6's cancel, and you still get 2 plus square root of 3. The same answer. I don't care whether you factor it or cancel it independently, as long as you can get it right. If you had something like this, 12 plus 7 square root of 3 over 6, if you say 12 and 6 reduced to a 2 and a 1, that would be wrong because that 7, you didn't reduce it with the 7. You have to reduce it everywhere. So that would not be reducible, in fact, if you leave it combined. All right, deep breath. Let's look over this problem one more time to rediscuss it. We're going to do another one very similar to it, mechanically speaking. All right, so we said this time I went ahead and gave you the angle separated. Spoiler for B, I'm not going to do that again. And we said, okay, well, we can say that formula goes tan, tan, 1, tan, tan, with a plus and a minus based on this plus. Then we did our very, very, very simple trig evaluations that the tangent of pi over 6 was square root of 3 over 3, tangent of pi over 4 was 1. We just plugged those numbers in their appropriate places. We simplified where we could, and then we said, oh no, we got fractions inside of fractions, and all these pluses and minuses really mess up the game. So let's clear out the mini fractions by finding the LCD and multiplying all of the bits by it, because that will get rid of the fractions. This is very similar to when we have an equation with fractions and we multiply everything by the LCD to get rid of the fractions. Same exact concept, just applied in a different manner. We got a much simpler looking thing, and some people will stop here and say it's the answer, but unfortunately it is, pun intended, radically different from the true answer, because you're not supposed to have radicals, square roots, in bottoms. And the reason is because maybe this thing is going to be adding some other number, and right now you'll go, well, I can't add that. But in reality, when you clean it up, maybe you can combine it with this other thing that might be over there in a bigger picture problem. Then, to do this, we had to remember how to rationalize denominators of binomials with radicals, which means multiply top and bottom by the conjugate. FOIL, clean it up, clean it up, clean it up. It's all algebra. It's nothing super advanced. It's just remembering all the little bits of algebra you were taught maybe a semester ago, maybe 5 years ago. I don't know. All right, tangent of 15 degrees. We might get one more problem in after this. We'll see. So this one I did not give you separated. You have to go, all right, well, I don't know a triangle with 15 degrees. What are these sides? I have no idea. So you can't take that approach. You go, all right, the basic approach doesn't work. Well, the next step up is the sum and difference formulas. Well, I could use 45 and 30 in this, and we know how to handle 45s and 30s. So we change it to the tangent of 45 minus 30. Third time we've seen that one today. There we go. And then we apply our formula, which goes tan alpha tan beta, then 1 tan alpha tan beta, with the pluses or minuses going there and there. And here's our combined formula, where the top sign takes the same sign as it originally was, the bottom one switches it. So we go tangent of 45 degrees. The top one takes the same sign as we said, so plus the tangent of 30 degrees, then over 1. This takes the opposite sign. Now I've made a mistake, haven't I? Because I'm looking up here and I saw that plus. The original sign was a minus, whoops, and I wrote plus here, so that was a mistake. Again, I had a mistake right here. That should really be, I still want to write it as a plus, minus, because this is a minus, this is a minus. Then 1, now this one will be the opposite sign, so it goes plus, and then this is the product, tangent of 45 degrees, tangent of 30 degrees. Now we already said tangent of 45 degrees is 1. What's the tangent of 30 degrees? We can pull out our other triangle. Here's our 30 degrees. Tangent is opposite over adjacent. Oh, we used 30 last time. Never mind. It was. I was thinking we used 60 last time, but we did use 30 twice, and that's just because I still had this circled. But that's just arbitrarily circled. Come on, what are you doing? What are you doing to me? Go away. There we go. And we're here, 30 degrees. Tangent's 1 over square root of 3, but we already know 1 over square root of 3 is square root of 3 over 3. Again, same information as before. It's just we had it in radians there. Now we have it in degrees. It doesn't really matter. They're interchangeable, except when we talk about inverse functions, essentially. So this becomes the tangent of 45 is the 1, minus the tangent of 30 is the square root of 3 over 3, all over 1 plus tangent of 45 is also 1 times tangent of 30 is square root of 3 over 3. 1 times anything is the anything, so this is 1 minus square root of 3 over 3, all over 1 plus square root of 3 over 3. Oh, we got individual fractions inside of bigger fractions. The pluses and minuses means we can't just say this is a fraction divided by another fraction and multiply by the reciprocal, because finding the reciprocal of this is extremely complicated. It is not 1 plus 3 over square root of 3. So this is where we said find the LCD of the individual denominators. The only individual denominators are 3s, so the LCD of those is 3. So we take what we had, 1 minus square root of 3 over 3, all over 1 plus square root of 3 over 3. A lot of similar things in this problem, aren't there? And the 1 gets a 3 as a product. 3 square root of 3, I'm sorry, the square root of 3 over 3 gets 1. This one gets 1, and this gets 1 as well. I didn't multiply top and bottom of the individual fractions, just the tops of the individual fractions. Now I'm multiplying the whole fraction, the big fraction, top and bottom by 3, but it only goes into the tops of the individual fractions. So those 3's cancel, those 3's cancel, no more individual fractions necessary. The 3 times each of those ones on the left are 3's. That's 3 minus square root of 3 over 3 plus square root of 3. Oh, wow, this looks kind of familiar. We have a bottom. This still has a square root, but there's a plus or minus involved, so we got to do that conjugate business. So we're going to multiply top and bottom by the conjugate. So we're going to multiply t and b, top and bottom, by 3 minus square root of 3, because that's the conjugate of 3 plus square root of 3. Again, when I figure out the conjugate stuff, I don't look at the top at all, because we're not trying to make the top fit some form, we're trying to make the bottom fit a form. Multiplying by the conjugate is what makes the bottom fit the form. There we go. So what do we have? 3 minus square root of 3 over 3 plus square root of 3, multiply the top by 3 minus square root of 3, multiply the bottom by 3 minus square root of 3. Top and bottom, the multipliers are the same. And then we just FOIL, 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 FOIL. We'll go a little quicker this time. For the first, that's 3 times 3, which is 9. In the top. For the outer, that's 3 times negative square root of 3, which is minus 3 square root of 3. For the inner, that's a negative square root of 3 times 3, which is another negative 3 square root of 3. Remember, you should put the rational number in front of the irrational number. The last is negative square root of 3 times negative square root of 3, which is positive square root of 9. Watch your pluses and minuses all over. Again, that was a negative times a negative, which made it a positive. Now, if you get really comfortable with this stuff, you'll know I'm not even going to multiply the outer and the inner, because I know they're going to cancel. Now, I'm comfortable enough, but I'm still going to show all the work for y'all. 3 times 3 for the first is 9. All these 9's cancel. No, don't try and do that. Maybe they do, maybe they don't. Just depends on what happens everywhere else. The outer is a negative 3 square root of 3. The inner is a positive 3 square root of 3. The last is positive square root of 3 times negative square root of 3, which is negative square root of 9. The outer and the inner will cancel. Again, I'm going to erase the cancellation symbol. You can keep it in your notes, but I'm trying to have something for students later. In the top, you got your 9. This minus 3 square root of 3, this minus 3 square root of 3, they stack. That's like negative 3 minus 3, which is negative 6. But you leave the square root of 3. Don't make that a square root of 6. The inside doesn't change. Then at the end, the plus square root of 9 becomes a plus 3. Again, these were combined. The 9 in front didn't change. The square root of 9 at the end changed to a 3. In the bottom, the outer and the inner cancel, so you have your 9. Then the minus the square root of 9 is a minus 3. The 9 plus 3 in the top is a 12, so you get 12 minus 6 square root of 3. 9 minus 3 in the bottom is 6. Very, very, very coincidental in the cancellation here. However you cancel it, 6 goes into all of those, so we divide all by 6. 12 divided by 6 is 2, minus 6 divided by 6 is 1, so there's still just the square root of 3. And then you might go over 1 because the 6 divided by 6 is 1, but you don't really need to write that. You really shouldn't write that as an answer. My math app will mark it wrong and you'll be pulling out your hair probably. Now the good thing is if this is a test, if you write this as the answer on a test and you tell me, hey, Mr. Beckner, can you look at this? I'm pretty sure that's right. And I'll go, yeah, you got it right. I'll give you full credit for that. But just please try and get it right without me having to take extra time to do that. Remember, we don't leave things over 1 in general. It's not simplified. All right. We got 10 minutes. Dang, I don't want to start this problem, but I don't think I can finish it either. I'm still here, I'm thinking. And I know as I think I'm wasting time, but oh, I tell you what, I am going to actually cut y'all out early for once because there's no way. I don't want to do half of this problem because I'll have to just redo the first half to do parts B or C anyways next time. So it's just going to be time lost. But I will go ahead and write the problem down. So we'll write the problem down. And then we'll call it a day. Stop it. All right. Example, what are we up to? 4? Yes. Given that the sine of a first angle alpha is equal to 4/5. I'm telling you the sine, I'm not telling you alpha, I'm just telling you its sine is 4/5. And that alpha is in the first quadrant, and that the sine of beta is equal to 7/25, but beta is in quadrant 2, excuse me. That wouldn't even be possible because the sign would have had to be negative. We're going to find, for part A, the sine of alpha plus beta. For part B, the cosine of alpha plus beta. And for part C, you might be able to guess it, the tangent of alpha plus beta. Now I could do a D, E, and F and ask for the sine of alpha minus beta, the cosine of alpha minus beta, and the tangent of alpha minus beta. I'm not going to though. The problems are almost identical. It's just a couple plus or minuses that change, really. Now, what you might think is, Mr. Beckner, you didn't tell me what alpha is, you didn't tell me what beta is, so how am I supposed to apply the formula and figure out the sine, cosine, cosine, sine, or cosine, cosine, sine, sine patterns and all that? How am I supposed to figure out these evaluations? Well, even though I didn't tell you the angle, this is enough to construct a right triangle out of and find the third side of that right triangle. This is enough to construct a second right triangle, so you'll have 2 of them, but you'll have to note that beta's in quadrant 2, so there's some pluses or minuses that might be thrown off because of that. And then from there, you can apply those formulas we gave you earlier, because even though you'll have some like a sine of alpha times a cosine of beta in one of them, while you don't know the angle, you know the sine of alpha is this. You can determine the cosine of beta based on the triangles that we're going to draw. So again, the idea here is we're going to draw a triangle for alpha, we're going to draw a triangle for beta, but we have to make sure we know what quadrants they're in because these are going to be reference triangles specifically. So alpha would be a 4 here and a 5 here. We've got to figure out that third side. For beta, this would be a 7 and a 25, and this would be an unknown side. So that's what we're going to be doing next class, but we're going to go ahead and call it there because, again, I don't think we can finish this problem in 5 minutes. So if you want to try that on your own, it's really not the end of the world, but again, make sure that you understand that beta is in quadrant 2, because when you're doing sines and cosines of beta, maybe one's a plus, maybe one's a minus, because it's in quadrant 2. All right, so we'll call it a day there. Have a good one. Remember the 6.1 homework is due this Wednesday by midnight. I did put that homework due date in there. 6.2 will finish next class and then would be due a week after that. The upcoming test for the next test we'll have is going to only be on this chapter, on chapter 6, and it's only 4 sections. So I'm going to go ahead and mention that test 2. Oh, I'm on eraser. Test 2 is just going to be 6.1 through 6.3 and then 6.5. We're going to skip 6.4. I'll actually upload some notes for 6.4 in case you're curious about it. But we don't have any homework and we don't test on it for some reason. It's wonderful information. It's something that can be applied in calculus, which is why I will give you access to notes, but I won't take time in class to do those notes. Yeah. So again, just going ahead and letting you know, it's only 4 sections on this next test. So it won't be too far away, maybe in like 2.5 weeks, maybe 3 weeks, something like that. All right, so we'll call it a day there. Even if you have any questions, get on that homework, study, memorize what you got to memorize, know how to apply what you got to apply, get your pre-calc 1 skills up to par, your rationalizing of denominators, your fraction stuff, your LCDs, because it's all here. All right, have a good day.